Moss here. We're going to continue our discussion of the water cycle, and now we're going to look at what happens to the precipitation once it hits the earth. Well, we mentioned in our previous video that it can run off. If it's not able to go into the ground, it may puddle up or flow over the earth's surface. That's called runoff. The other option is to go into the ground, and that's called infiltration. Now, infiltration is dependent upon a few characteristics of our Earth. First, we're going to look at something called porosity. Now, the porosity is the percentage of an open space or a pore space between particles of a material. Now, you may have heard the word pore before on your face. The little holes are pores. So pores are little holes. And when you have dirt and a material of the Earth, there's some pores or spaces in between those particles, and that's what we call porosity, the percentage of the open spaces. It's also going to depend upon the permeability of the earth. And permeability is the ability of a material to have water pass through it. So those are the two key components to what's going to allow water to infiltrate or seep into the ground. And we're going to look at this a little more closely. Let's take a look at porosity. There are a few factors that will affect porosity. The shape of the material. If it's a rounded particle versus an angular particle, you will see they have differences in their pore spaces. So if we look at the two pictures, rounded or angular, well-rounded particles have a greater porosity. You can see the spaces in between each particle. Whereas if it's made on an angle, those spaces get filled because they're flatter next to one another. The particles pack together a little bit more, and we're going to get into that next, packing. Well, if it's closely packed together, you see on this side of the diagram, there's not as much pore spaces, whereas if it's loosely packed together or not as tight, then you'll have more open spaces. So the more loosely packed the particles are, the greater the porosity. We also have something called sorting in our earth and our materials, and this is what happens when we have some particles that get thrown together through different various processes, and they either can be sorted with similar shape objects and the same size objects, and that very neatly packed together, these are considered to be well sorted. Whereas if we have an unsorted bit of material, the larger pieces get fit in with the smaller pieces, and the small pieces fill in those pore spaces. So it becomes very, there's low porosity in a unsorted piece of material. So well-sorted particles, or the small, similar shape and size, have a greater porosity. So when we continue to talk about porosity and we look at that and we think about the pore spaces, we look at two samples like this. This is the same size parcel of material. One is sorted with large particles and one is sorted with small particles. So which one will have the greater porosity? Well, this is actually a trick question because they're both going to have the same amount of porosity, believe it or not. The smaller particles and the smaller pore sizes of this equal the larger pore spaces in the other because there are more smaller particles, or smaller spaces, I mean, and there are fewer large spaces. So the pore spaces actually equal themselves. Therefore, size has no effect on porosity if the shape and the packing and the sorting are the same. Okay? Once something else changes, then the porosity will change, but size will have no bearing on porosity. They equal the same amount. Well, now let's look at permeability. And if you remember what we said, permeability is the ability for water to pass through the material. So if a material is permeable, water is able to pass through it, and the opposite is true as well. If we consider it impermeable, if water cannot go through. An example of this is bedrock. That's something that our earth is built on. It's deep underground and water cannot penetrate it. So the three factors that we've already discussed that enter with porosity will also come into play with permeability: packing, sorted, and shape. Factors that affect permeability, again, are going to be the pore size. The larger particles have larger pore spaces, so the permeability will increase because water is able to move through that material more freely. We also have interconnected pores, and in order for water to be able to pass through the material, they need to be connected, so it makes a larger space. Once that space is connected, the water can pass through. The amount of precipitation that infiltrates or runs off will also depend on several factors. Now, if the soil is already saturated and holding the most or maximum amount of water that it can hold, there will not be any infiltration occurring. Water can't go into it anymore. It's already filled to capacity. We call that saturated. Example, the sprinkler in the lawn. So if you have a lawn and you've seen the sprinkler on for way too long, you'll start to see puddles forming, and that's called saturation of the soil. Once it's already filled to capacity, it won't seep in anymore. Also, the slope of the land is going to affect whether or not water will infiltrate or run off. The steeper the slope on the Earth's surface, or the gradient, then the less infiltration occurs, which makes sense. Water can't run off of it if it's at a slope and it's going to be moving, and gravity is going to be pulling down on that water to make it go along the surface. So we will say, though, that runoff will increase. So in the gentle slope, we can have infiltration. Steep slope, no infiltration. Water will run off of a steep slope, but infiltrate into a gentle slope. Less runoff occurs on a gentle slope. Now here's just a beautiful picture of a waterfall, but you see the slope of the land here is actually pulling that water down, causing runoff. We would not get much infiltration into that material. Now the rate of precipitation will also affect whether or not water will infiltrate or run off. So the rate of precipitation, meaning the speed at which the precipitation is coming down. So if the rate of precipitation is greater than the rate of infiltration, meaning if it's raining more than it's going into the ground, the water won't be able to infiltrate, and so we'll get more runoff and flooding will occur, as in these two pictures. Here's another picture of runoff. You see the slope is coming into play on this one. Now, this brings us to something called capillarity. Capillarity is also a movement of water, but it's the upward movement of water. It's when it goes against gravity and moves up a certain material. Now, this is due to the molecules being close together, so it allows the water to stick to it and move upwards. We see this in roots of plants. That's what allows the water that's at the bottom of the plant to give nutrients and come up to reach the top of the plant. Capillary action causes water to rise upwards from the water table into the zone of aeration. We're going to get into those levels of zones in just a moment. But in this instance, with capillary action, the smaller particle size, the greater the capillarity. If the space is too big or wide, then the molecules can't cling to one another and move upwards. So it has to have a smaller size material for the capillarity to work. Now let's get to those zones that I mentioned, subsurface zones. This is underground. Now we're looking underground, and there are three zones that we have underground. First, underneath our immediate surface, we have what we call the zone of aeration. Now this has the word air in it, zone of aeration. So air means that the aeration means there's particles mixed with air at the top of the surface. Now that makes sense, right? Because it's close to the air, it's close to the atmosphere, it's up right underneath the surface. So air gets mixed in. Underneath that, we have the zone of saturation. And if we go back to see and think about what I said saturation means, when a substance is completely filled with water, it makes sense then that the zone of saturation is where there is only water. It's just a zone of water that's underground. Now, the two boundaries meet right at what we call the water table. The water table is that line, that boundary, or that interface that goes between the zone of aeration and the zone of saturation. And in this instance, it's along here. Now, one thing I want you to take note of is that it will actually follow the shape of the land. The water table follows the shape of the land. So this goes downhill a little bit towards this little hole, and then you see the water table follows that as well. Okay, let's take some notes on this now. We have the zone of saturation and the zone of aeration. And there's a capillary fringe that allows the water to go upwards towards the upward of the landscape. Now, water can infiltrate as far down as the zone of saturation, where all the pore spaces are completely filled with water. And above this layer is the zone of aeration, which contains both water and air. And the interface or boundary between these layers is called the water table. Okay, so this is important. You need to know this. You also need to understand that the water table can rise and the zone of saturation can grow with more precipitation that we get. We talked about having a water budget with a surplus of water. That's what would happen with a surplus of water. When we have more precipitation coming down and seeping into the ground, it can actually raise the water table and the zone of saturation. The opposite is true too. If we have a drought and we have the less precipitation coming in and we are using water that we use underground, what you'll notice is then the zone of aeration will start to grow and the zone of saturation and the water table will lower. So that's all going to depend on our water use and our precipitation levels and our potential evapotranspiration, as we've been discussing with the water budget. So that's the end of our groundwater video. I'm going to leave you with this groundwater link, and hopefully you will enjoy the song.